So, hi everyone. I'm Francesco Cremonesi. I'm substituting Marco Lorenzi, who could not be here, unfortunately. I will be presenting to you Fed-BioMed. This is a project that's been mounted at INRIA right now. It's a federated learning framework, so something that aims to be a little bit larger than a library, and it has a specific focus for biomedical applications. So to give a little bit of context, one of the main challenges that we have in dealing with medical research is that data is really scattered, it's really heterogeneous, and there's a big problem with reusability. So as you can imagine, every hospital does their little experiment in their corner with 50, 100, 500 patients, but then there's no really there are no big, let's say, ways of sharing this data and doing collaborative science that are well established right now. And so the first idea would be, how can we centralize this data? But there are some big limitations, especially in the medical field, for centralizing data. One of them, I think everyone has had a brushing with this at some point, is the GDPR. So medical data is really sensitive data that affects the privacy of people, so you cannot just share it with anyone or move it around as you like. And there's also, let's say, political barriers, economic barriers. It costs a lot to generate this data, and maybe hospitals are not always incentivized to share it, and so on. So this is where a federated approach could come in handy. So the idea when we do federated learning is that the data will always remain within the institution where it was generated, or the source institution, and the only thing that is being moved around, passed around in the network, are the parameters of the model. So these are some sort of aggregate, very, very high-level aggregate of the data, and therefore it's okay to share this information. So this is just to give an idea. You have 4 hospitals here who want to participate in a federated learning experiments. Each one of them has their own image, and how it works is that they will train some model locally. So they need some compute power or something locally at the hospital. They need sort of a version of a software that is able to do this kind of training at the hospital. So this is one of the challenges. I'll talk about it later. But then they train a local version of the machine learning model that they want to create, and then each local version is shared centrally within here it's a central hospital server, but it doesn't need to be a hospital. It can be any sort of centralized server, and then there is a, let's say, a smart mathematical way to combine these models into what is called a global model, an iteration of the global model. And then we have now reached the point where we have one global model. This global model is shipped back to each hospital, who can iterate, who can train, let's say, for a few more epochs with using only their own local data, starting from the global model, to reach another iteration of their local model, and then they share it back centrally. A new iteration of the global model is created, and this goes on. So you see, it's an iterative process where the training happens locally at each hospital. Then the hospitals share their data, they share their model centrally, and a unique version of the global model is created. And then if needed, this unique version is sent back to the hospitals, and more training can happen. And what are some challenges when we want to apply this process? Well, we've talked about the heterogeneous data, obviously. Every hospital has their own data format. If you've ever worked with hospitals, you know what a pain this is. Then, of course, we need to take care of security. So this is, security at the hospital, security of the machine learning algorithm, security when we move the machine learning algorithm around, security of our network, and so on. So there's a lot of facets of security that need to be taken care of. Then there's an issue of governance. So where are the servers located? How much can the researcher who wants to, let's say, execute this federated training, what kind of control do they have on what the hospitals are going to do? And conversely, how much can a single hospital sort of veto, for example, some kinds of training or some kinds of models and so on. Then we have an issue of, at each hospital, we need, as I mentioned before, computing resources, and something that we are learning in the hard way is we need a lot of personnel time as well, namely for formatting data, which is different, as I said, in all the hospitals, to a common format to enable the training. And then the obvious challenge that we have as well is that there's all sorts of regulations, ethics committees, and so on that we obviously need to take care of. So there's a lot of very, very good federated learning libraries out there. For the sake of time, I took out the slide, but there's NVIDIA, there's IBM, Flower is a very good one, Intel have OpenFL. I mean, there's lots of very good ones. So why do we need yet another one? Well, we think that Fed-BioMed really responds to the specific challenges of handling biomedical data, and we are designing it, we are creating it on the basis of these 5 pillars. So the first one is giving control, as much control as possible to the hospitals in terms of governance of the data and governance of the machine learning models. Then we want to facilitate the integration with biomedical data sources, so by trying to respect medical interoperability standards and so on. At the same time, we want to allow data scientists as much interactivity as possible while they're running this federated learning experiment. So Fed-BioMed is trying to position itself as a framework for medical research. We don't want to position ourselves so much as something where we have like a production-ready batch execution of experiments that is integrated in a clinical decision support system. It's more something for running research experiments, so asking questions about, can I predict some diagnosis of patients based on their medical data and so on. Then, of course, we have the privacy and security pillar. This goes without saying. And another thing that we want to emphasize is that we are not creating a product for research on optimization or research on federated learning itself. We really want to focus on the deployment of medical research in the real world. So our focus is very much geared towards the hospital users, the clinical users, and so on, and not so much, slightly less, let's say, on the researchers who are more interested in discovering a new federated learning algorithm. Okay, fancy transition, sorry. To speak a little bit about how Fed-BioMed is organized, we have 3 main components. These are the nodes, so it would be the hospitals in what I've been saying until now. They have the data and they do the training. Then we have a central network component, which basically is a broker for the communication among the other components. And finally, we have what we call the researcher or the data scientist. It is basically the driver of the federated learning experiment. They decide, which kind of model to use and so on. And the aggregation right now in Fed-BioMed happens at the level of the researcher, but we may think at some point to move it to the centralized network. This is kind of a small detail. So if you remember the slide from before about the introduction to federated learning, this is how we are implementing it. So starting from top left, you can see it's kind of a cycle, and this is reflects the fact that it's an iterative process. And it works as I tried to explain before. So the researcher initiates a training, then we have a local phase on each node where the training actually happens. And the way the training is triggered is through network messages. So the training happens on the node. each node creates their local version of the machine learning model, and then again through network messages they send these versions of each local model to the centralized aggregator who performs the aggregation, and then if needed the iterations continue. And to give you a little bit of an idea of how we are reflecting those design pillars that I said in the beginning. So we have a system that allows to integrate different kinds of data. We are sort of implementing the different Python classes ourselves that are an interface to common data standards like nifty images for image segmentation, for example. This is a good example. And what happens is then we have created a web GUI which is hosted on the hospital. So it's not something that can be accessed by any outside network. It's just a way to simplify the manipulation of the database for clinicians. We've created this GUI, and this allows them to basically sort of click and select different data sets that they want to earmark for sharing. I should not say sharing, rather for the training of this federated algorithms. And then we also allow each hospital fine control over which kind of training can happen. So they are allowed to veto certain kinds of parameters and so on if they don't want those to happen. They can add and remove data sets at any time. And one feature that we've implemented recently is that we allow a way for hospitals to review the code that may get executed locally, and they can approve it or reject it. This is kind of a controversial thing because you won't always have sort of data science experts on premise at the hospital, but for now we're doing it this way. As I said, we have this interface to medical standards, and the way we work is that when data is added to the database locally for federated training, then the clinician adds some sort of tags, and these are the tags that are used by researchers to identify that specific data set in the whole federated network. So when the researcher wants to execute, a specific experiment on the cancer imaging data or something like that, they need to have agreed beforehand to use a specific tag which would be the same over all the hospitals, and then this way they can, let's say, reference the data. And we're still, meeting a lot of challenges here. So one thing is, as I said, hospitals all have their own different IT infrastructure, so it's really difficult to have a unique way of let's say, grabbing data from there. For now, it's a very manual process where we ask clinicians to manually prepare the data sets that will be used for federated learning. This is a really painful process. And then another thing that we're learning is that not all hospitals will have the same sort of computing infrastructure in place. And so within one experiment, you may have one hospital that is able to train on much more data or finish quicker. And then you kind of have to wait until the last hospital is finished. These are kind of common problems in parallel processing in general. But in the interest of time, maybe let's go quickly over this. Researchers have a notebook, Jupyter Notebook interface, and we give to them this class called the training plan. They define which kind of model, which kind of optimizer, and so on. We also give them a little bit of leeway in terms of defining how the federated learning experiment takes place. So this is what we call the strategy. It's not as advanced as, let's say, you would find in other frameworks like Flower and so on, but we still give them a little bit of idea. And then they can monitor how the training is going through an interface with TensorBoard. And the one thing that I want to point out here is that the code of the training plan is written to a file and literally shipped over the network to the different hospitals. This is something that we do a little bit differently from several other frameworks, mainly because we want to enable this sort of interactivity. So we want to allow the researcher to, change, iterate over the code quickly. But obviously this comes with security, let's say, concerns as well. There's a lot of different ways in which security can go badly in federated learning. We've done some good work on some of these, so we are able to deploy Fed-BioMed in a VPN environment, which is kind of sandbox and isolated from any external attacks, potentially. We have this feature of approving the training plan code, and we also have differential privacy in place. And we are working on secure aggregation using multi-party computation. So this is more about strengthening your machine learning models from, attacks. And what we still haven't implemented, but it's in our roadmap, is having a secure encrypted communication inside the VPN network as well to prevent man-in-the-middle attacks. So, final slide and real reason why I'm here presenting today. Fed-BioMed is a small-ish project who's looking to grow, and we want to grow in terms of open source engagement, potentially creating a community of contributions, and then in the future maybe even creating a consortium. And so I'm here to kind of advertise our existence to the world and also ask for any sort of experience, feedback, any ideas that you might have, and what are some good ways in which that we could grow, and also to elicit your participation in the community. So please go to the GitLab pages, go to our GitLab repository, and start it and so on. Thank you so much.
Thank you, Francesco. Maybe your first contribution to Fed-BioMed can be a question.
Yes. Yeah, thank you for the presentation. I have a question about privacy. I wonder how you explain to the user what the privacy mean, what the privacy budget mean, what they lose by using the differential privacy. Do you have an insight for measuring that?
The short answer is no. The long answer is obviously we show them many examples as much as possible. We try to sort of engage them in understanding the trade-off between, on the one hand, protecting your data better, and on the other hand, losing maybe some accuracy or something in terms of the performance of your model. And then we just hope for the best that they understood.
Thank you.
Thanks.
One more question?
There is any possibility for nodes to kind of manage how the computing power of each researcher will be managed? I don't know if my question.
Can you give me an example, or
how hospital can manage each training, how they give power to each training, or?
So right now we run in a very sort of simple, let's say, framework where on each hospital experiments are just run sequentially. So inside each hospital, you will always have the full computing power, and if there are multiple experiments that want to be run, it will be one after the other. Although, to be perfectly honest with you, we're targeting more a situation where you would have one experiment running at a time. We're sort of imagine there is like a consortium for running an experiment on cancer data. Then let's say the design space of Fed-BioMed is on this specific week, the hospitals will activate their Fed-BioMed servers, and then for 1 week, the researchers can run experiments there, and then those servers are shut down, and we wait for like So it's not really something that is always on and kind of high availability.
Thank you very much. So you can continue to talk to Francesco later on. There is also David Marjorie in the room, who is really aware of other INRIA open source projects. So feel free to talk with both of them. Make some noise again.
Thank you.